Hi, this is Graham Helfrich with IHS Markit. We're going to have a look at the new Multiwell Reservoir Model that's available in the Harmony Enterprise software. So, historically, creating a reservoir model for more than one well has been impossible in our reservoir engineering software, whether it's Harmony or Harmony Enterprise. And this meant that you couldn't consider the impact of one well on another in the reservoir. So in this presentation, we're going to focus on two case studies highlighting the advancements we've made for multi-well reservoir models. Everything you're going to see is using our Harmony Enterprise software. It's version 2018.1. Now it's important that with Fiquet, which ISS acquired, that our objective was always to make practical and easy to use software. So I'm really proud to say that we have made a powerful multi-well reservoir model that the average engineer can now use. And I want to prove that to you today. So let's start by reviewing some of the differences between an analytical model and a numerical model, because we're going to be using the numerical model for all of this multi-well reservoir modeling. Here we have an analytical model. And analytical models are single phase, meaning that they can look at the oil, but they will ignore the gas production in the reservoir, or they'll focus on the gas. So single phase means we're going to be ignoring relative permeability curves and changing saturations through time. Well, the benefit of an analytical model is how fast they are. So here we have a horizontal multi-stage fracture well, and on the screen I'm changing my fracture half-length estimate. Look, below we're getting an immediate response in our history match. We can do this right on the fly. This is why analytical models are so excellent. We can get feedback to see if any of our reservoir inputs, permeability, skin, fracture half-length, etc., if those are giving us a better history match or a worse history match. We don't have to wait around. Okay, so as we get a little bit closer, we can tune this a bit more. We even have the option to select, for example, permeability and ask the software to automatically tune it to match the history. Okay, so again, this is another benefit of analytical models, how fast they are. They're very practical and powerful. But what about a long-term forecast? Okay, here I have an analytical reservoir model. This is a vertical well in the center of a square reservoir. So this is what we call a test design. No production history, but I just want to do a hypothetical forecast of production. So I've entered my dimensions, my drainage area, I've got my permeability entered, my skin, and we can do a forecast from this. So my initial rate is about 800 barrels per day and my oil rate is expected to decline. I don't get an estimate of gas or water from my production forecast. It's because this is an analytical model. It assumes single phase flow. Now if I want to, I can change my estimate of permeability. We see how immediate the forecast is updated. Again, the beauty of analytical models. Well, what about a numerical model? So that is built into Harmony Enterprise. We can simply go we select the word hybrid. Hybrid is what we call our numerical model because it's so fast. It's almost as fast as an analytical model, hence the word hybrid. So we can do black oil, gas condensate, or volatile oil. For gas condensate wells, we actually use the Ovalier correlation to predict condensate dropout from the gas in the reservoir. So in this case, we're going to be picking black oil, and we have the exact same reservoir I've described here, but now this is a numerical model. It looks the same, right? Well, there's actually gridding set up. We're going to see that. And the permeability I use here is the absolute permeability now, where an analytical model we use the effective permeability. This numerical model we're looking at here uses the relative permeability curves that are available here. They're all set up by default, but you can change them if you want. So let's run a forecast here with the numerical model. We see the pressure changing, the saturations changing at different grids and cells in the reservoir. And here is our numerical forecast. So we get a declining oil rate, but we also get an output of our water rate and our predicted gas rate into the future. We can see how the GOR is expected to change in the future as well. And just like an analytical model, we get the average reservoir pressure expected into the future. And if we want to, we can also add Monte Carlo risk analysis or probabilistics to estimate our range of forecasts when we have uncertainty for any of our inputs like permeability, net pay, etc. How do these two models compare? Well, analytically, this is the rate time forecast we get here. The higher forecast is the numerical model, and it's higher because we're getting the solution gas coming out of the oil, helping maintain the energy and pressure in the reservoir. The same plot, but on a cumulative format. We see our single phase analytical forecast here and our multi-phase numerical forecast here. So in this case, the numerical model is giving us a higher EUR. Every case is going to be different, whether it's gas condensate or oil based on the bubble point, everything like that. But this is one example I just wanted to show you. Okay, so that's a little bit of background on the difference between an analytical and a numerical model. Let's look into our case studies now. So we're going to correct a few perceptions on the way through this example. One is that setting up a multi-well reservoir model is complicated and it takes a lot of time. Another perception is numerical models run slowly. Another perception is from IHS Markit, we only have single phase models. Well, hopefully I've already partially proven to you that that's not accurate with what we just saw here. Let's jump into this case study. So I've got this well down here in the southwest, and this is actually the well we just looked at. We forecasted it using the numerical model. We got our forecast. But now I want to consider what would happen if I had other wells around it. How would the interference between those wells affect their production and the forecast for this entire reservoir? So I've put some wells on the screen here. You can see everywhere I move there's a latitude and longitude. This is how we're going to determine the position and the distance of these wells from each other in the reservoir. Now I need to give these new wells some basic inputs about fluid properties, net pay, etc. And I'm going to be lazy and I'm just going to copy those parameters from my existing well that I've already forecasted. Okay, so I'm applying those petrophysical parameters and fluid properties to these new wells. That's all done. Now, from the group level, with those 3 wells, I can go multi-well. And here we go. We've got those 3 wells. And again, their position is based on where they are on the GIS map. If we blow this up, we can see the gridding is already set up for us automatically. Now these lines between the wells, these are not no flow boundaries. For this particular well, I'm going to give it a permeability of, in this case it can be 10, and a skin of +2. And it has a net pay, it has porosity. So these parameters, this is where they apply in this area here. This well can have a different set of permeability, of net pay, etc. And this is where those properties are applied to. So the pressure will cross this line into another area. This is not a no flow boundary. It just defines where these reservoir properties apply. For this well, our permeability is 4.4. Our skin will be 0. And this last well, I'll give it a lower permeability but a negative skin, and maybe I'll change the net pay and I'll increase the porosity a little bit. Okay, so these properties can differ between the wells. I want to make sure I'm going to be considering all the fluids in my forecast, and now we need to set up some rules for the forecast. How long do I want it to run? Well, I'm going to run it for 10 years, and I'm going to flow each of the wells at the same bottom hole pressure of 1,500 pounds. All right, we're ready to forecast. Here we go. Okay, so we're looking at the pressure distribution through the reservoir. It's actually done already. It just did a 10-year forecast that quickly. So if I rerun it, this time I'm going to look at the gas saturation through time, or oil saturation, or water saturation. We can see how this will play out into the future. So what does a forecast actually look like? So on the top right, this is the total forecast combining all the production from the wells, gas, oil, and water. The top left, this is the production forecast for each individual well. So one of the wells, its initial rate will be around 1,000 barrels per day. Another well, it starts even a little higher. Another well starts a bit lower, so we can see that for individual wells here. Below, this is our GOR and water oil ratio expected into the future. So this is one scenario, but there's going to be some other things we want to try. For example, one of them is maybe I want to modify the boundaries of this reservoir. I don't want it to be a simple square. Well, we can very easily drag this on the screen and change it, and we can actually look at the grid cells to see how they're automatically created for us. Okay, so I'm kind of changing my reservoir boundaries here. Now, another thing I may want to consider is, what if these wells begin production at different times in the future? All we need to do is go set up that description in our forecast. So I'm going to break these wells up so that they come on in 40-month increments. To help save me a little time, I've got this scheduler. I'm going to copy and paste it. And what this says is that this well will begin production right away, and it'll keep producing at 1,500 pounds bottom hole pressure. This other well will actually have no rate for the first 40 months, and then it will finally begin its production at this drawdown. The third well, it has to wait 80 months at a rate of 0 before its production will begin. So we've got this schedule set up here, and let's see how the forecast looks. So we see our progress on the bottom here, 30, 45%, looking at gas, oil, water saturation. It's done. That's how quickly it did it. So the result of this is now the total rate from the reservoir begins with one well producing. 40 months later, the second well begins, and later the third well begins. We can even look at the individual well forecasts again here, and then again that changing GOR and water oil ratio into the future. So this is a very simple test design, as we call it, just looking at predictive mode, not doing any history matching, but it's a starting point. So hopefully I've already addressed a couple perceptions here. One is setting up a multi-well reservoir model. It can be simple. It can be fast, as I just showed you. Another is numerical models don't have to run slowly. You saw how fast we were able to do this. And another is Harmony Enterprise is not only for single phase. As we saw here, it does multi-phase reservoir modeling, as we've just seen here. Now, in terms of our numerical model, how does it work? Well, and how does it run so quickly? There's actually a white paper I'm happy to send you if you want to email me. I'll include my information at the end. But the main difference is we actually use a pseudo pressure, and we use that to pre-calculate the fluid properties between each of the grid cells. That's the main component of why our numerical model is so fast. So again, I'm happy to send you that white paper, and we've benchmarked this against some of the main multi-phase simulators in the industry for reliability, and I'll be happy to share those with the white paper. It's included in there as well. Okay, case number 2. What happens if we add a new well among existing wells that are already producing, an infill well? So the background here is this is a conventional gas reservoir, vertical wells. There are 4 wells currently producing, and they have about 3 years of production history. This operator has a contract that expires in about 10 years, and that means we may want to consider accelerating the production. There's not very much shut-in data, so we can't do our traditional build-ups or our P over Z plots. So the production data is going to be needed. The objective of this is we want to come up with an EUR estimate considering the pressure communication between the wells in the reservoir. We want to come up with a new EUR if we were to drill an additional well, an infill well. We also want to try to quantify how much production loss are we going to see at the existing wells if we add a new well. All right, so we're going to get into this right now. So back in Harmony Enterprise, I've got these particular wells up here to the northeast, and these are the 4 wells that are producing now. I've already done an individual analysis on each well. I did my flow material balance, my type curves, my model, and the results of each individual well are kind of shown here on the annotations. Now let's try to forecast this and look at this in a multi-well reservoir model. So I've got those 4 wells here set up. I actually have the individual production history, rates, and flowing pressures for each well. And let's see how our history match looks. So now we're doing a history match, looking at the pressure through the grid cells here. Look at the water saturation through the history. We're about 60% done the history match. Okay, and we're done. So above we can see the history match and how good our pressure compares from the model to the actual history. We can look at another well and see how it compares. I can blow it up. So I've basically gone through with each of these 4 wells and adjusted the permeability and the skin and the area to try to make sure I've got a good history match. So I've got a pretty good model representing the history right now. Another one of these inputs here is the drainage area comes up with a total drainage area here, or total volume. One way I can confirm that is using a diagnostic, using the flowing material balance. Traditionally, we think about the FMB analyzing one well at a time, but we can also use it to analyze groups of wells. Okay, so I'm actually doing a group FMB analysis right now. And we can try to adjust this, make an interpretation here, see what we come up with. So in this case, I come up with about 6,300 acres, or about 480 BCF. And this is just a verification for when I'm doing my modeling, try to see if these diagnostics in the model support each other, which they are in this case. So at the end of this history, meaning today, how much pressure do I have left at different locations within the reservoir? Well, I've got quite a high pressure remaining right here. So this is where I want to consider drilling the infill well. Going back to the GIS map, all we need to do is position that infill well on the screen here. We'll add it to that group. And again, I'm going to give this new well some sort of inputs for net pay and porosity. And again, I'm going to be a little bit lazy and copy or clone those properties from an existing well and apply them to this infill well. There, it's all done. And we can see that on our reservoir model now we have a scenario with a new well. So I'm going to give this new well its estimate for our permeability for our skin. And now we can run a forecast. So let's define how we want to run this forecast. So when is this new well going to begin production? I'm actually going to wait 12 months before it begins. So for the next 12 months, this new well is going to have no gas rate. And then for the remaining of the 10-year forecast, I'm going to let it flow at a bottom hole pressure of 650 pounds. The other wells are just going to keep on operating at the same drawdown that they have been. So let's go ahead and run this forecast and see what happens. So again, we see the grid cells are set up automatically for us. It saves a lot of time. The progress, we're about 50% done. Look at our remaining gas saturations or water saturations. Okay. Okay, all done. So what are the results? So this is the forecast for the entire reservoir. We see that the 4 wells are producing, giving us this rate for the next 12 months. And then we see a increase in our production rate. This is because we've added the additional well at this point in time. We can also look at that individual well's forecast right here. But the big question is, what is the difference in our EUR for the field with or without the infill well? Well, I'm going to go to the comparison plot here to see that. So I've got time versus cumulative production. The red line is if we do not drill the infill well. We're going to cum about 240 BCF. The green line is the forecast or the cum with that infill well. And the difference works out to be about 25 BCF in additional EUR. That's great. That's one of the questions we were trying to answer. The other question was, how much will the old wells be affected if we drill the new well? It's easy. So the red forecast, now we're on rate versus time. This is for well number 1. The red line is if this infill well was never drilled, if we leave only the current wells producing. But if we drill the infill well, this well is going to suffer a little bit. So this is the new forecast it'll have. Well number 2, we see how much we're going to lose from it. Well 3 and well 4, how much we're going to lose if we drill the infill well. But the net difference is positive, as we see here. So another interesting output from this is, what does the average reservoir pressure look like with 4 wells versus 5 wells? So we see this is the red reservoir pressure through time with only 4 wells, or with 5 wells we can reduce it more quickly. So some key takeaways here are that for our numerical model, it considers multi-phase flow. It uses relative permeability curves. As you saw, it's also a lot easier to set up than other numerical models. And the speed is incredible, as you saw. This is a huge advantage. You don't have to wait to get these results. You can do more sensitivities. For our multi-well model that we've been focusing on here, number 1, it gives you a more accurate estimate of your EUR, considering that pressure interference between the wells. It lets you predict the impact of an infill well before you have to invest in actually drilling it, like we just saw here. There's a lot of other sensitivities we can explore, but we didn't today. One of them would be, what happens if we operate wells at a higher or lower drawdown? Can we accelerate production from one well versus another, and how will they impact each other? We can actually do history matching for each well in a multi-well reservoir model on both rate and pressure, like we saw. The grid cells are set up automatically, and that saves a lot of time and helps it run quickly, like we saw. We can also view those pressures and fluid saturations through time. But I think the most important takeaway from our multi-well reservoir model is it actually opens this type of work up to the average engineer. And I know in the past, multi-well modeling, it's been a bit of a specialized function, and it's used quite expensive simulation software. We've also heard that setting up these multi-well models, it takes a lot of time, talking about hours or days just to get to the point where you can actually do some forecasting. So what I've hoped that you've seen here today is going to provide you with a practical and efficient way to actually perform multi-well modeling with Harmony Enterprise for the average engineer. Let's talk about what's coming next. So what I've shown you has been available for a few months, and it's for vertical wells only. This is where we've started. I'm going to talk about where we're going and the other requests we've had. So in July of 2018, we're going to add the functionality to have wells that inject water or gas. So this will be good for pressure maintenance scenarios and history matching. Also, we're going to be adding pressure support at various boundaries in the reservoir. We've had a request for the option to change where one permeability begins and another permeability starts. So that line separating properties between the well. It's a default now, and people have asked us, can I change where that is? So we're looking at that. Vertical wells, this is not where we're ending. We're just starting with vertical wells. So in July, we're also going to have horizontal wells available in a multi-well model. These are not wells with fractures. These are conventional horizontal wells. By the end of the year, we hope to have this available for unconventional wells, for horizontal multi-frac wells in a multi-well scenario. We're also working towards multi-layer models for both conventional and unconventional, hopefully by the end of this year. That's going to be huge. We've been getting so many requests for this. Another request we've had is automatic parameter estimates. Back when we looked at the analytical model here, I showed you how you can select permeability and it will automatically iterate to do a history match. We've been getting this request for our multi-well model. We actually already have it for the numerical models, but not for multi-well model yet. We've also been asked to incorporate probabilistic Monte Carlo risk analysis, which again we have for single well numerical modeling, but we don't yet have it for a multi-well model. So that's been a request. If there's anything else that you'd like to see for our multi-well model, please let me know. Here's my contact information. Thanks for watching this. If you need access to Harmony Enterprise, contact your account manager or me. I'm happy to get you in touch with them. Any other questions, or if you'd like the white paper explaining how our numerical model works and how it's so fast, reach out to me. Thanks so much for your attention.